the last part of electromagnetic induction. The topic is mutual induction. So first of all, what do you mean by mutual induction? See, from the term we can understand mutual means between two things. Okay, so suppose we have two coils like this. This one is one coil, and we put a EMF with some rheostat. This, and with this, if we put one more coil in this way, and if we put a galvanometer, and suppose current will flow. So if we change the value of the rheostat, so that what happened, current vary. As the current vary, flux vary. So magnetic field passing through this one, as the magnetic field passes through like this, so due to that magnetic field passing through this one, so magnetic flux passing through this one, when the current change, magnetic flux change, and magnetic flux change, induced EMF will try to oppose it. So what happened, flux change in second coil depend on the current in the first coil. Similarly, when the flux change in the second coil, it generates EMF. So as it generates EMF, so current flow through this one, and due to that current, magnetic field passing through this one, so flux passing through this one. If the current change means the flux change, so again it will generate EMF. So that means if this is the coil number 1 and this is the coil number 2, so what we find is second coil depend on the first coil, and similarly the first coil depend on the second coil. So basically they are depends on each other. So that's why this is called the mutual induction. So basically what happened, the flux of the second coil due to first coil is directly proportional to current of the first coil. So when you equalize, we use mutual induction at 2 due to 1, current 1. Similarly, if we write flux at 1 due to 2 is directly proportional to current at 2. So flux at 1 due to 2 is equals to mutual induction at 1 due to 2 and current of 2. So mutual induction at 2 due to 1 is the flux at 2 due to 1 by current of 1. Mutual induction at 1 due to 2 is the flux at 1 due to 2 by current of 2. And in both cases, if we see in both cases M of 1 2 or M of 2 1, they are equal. So we can write it M. Later on we prove it that mutual induction at 2 due to 1 or mutual induction at 1 due to 2, they both are dependent on each other. So that's why 1 2 or 2 1 is equals to mutual induction M is equals to mutual induction M. So that means they have some common factors. Because of that, they are called the mutual induction. And SI unit, now if you see flux per unit current, so we can say Weber per ampere, or we can say Henry, 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 represented by H. So self-induction and mutual induction, in both case, self-induction and mutual induction, in both case, its SI unit is Henry. Is it okay, everyone? Case, mutual induction for solenoid. From that we get some more information. Like if you want to write EMF at second coil due to the first coil, that is minus flux at second coil due to the first coil by dt, and flux depend on this, the minus, we can write this one, minus M21 d1 by dt. Similarly, if we want to write EMF at first coil due to the second coil, that is flux at first coil due to the second coil by dt, that is minus m of 1 to dt by di2 by dt. So you understand from this you can find the EMF also. Is it okay, everyone? This portion, I think it's okay.
Yes, sir.
So now the next part is okay. We have to find out the mutual induction between the two coil of a solenoid. So suppose we have two coil. This is the first coil. And we have one more coil like this. So this is the first coil. The inner coil. And in between, we can put this one. In the secondary turn. This one is the secondary turn. And L is the length of the solenoid. L is the length of the solenoid. Now, N1 is the number of turn in the first coil. N2 number of turn is the second coil. A1 cross section area of the first coil. A2 cross section area of the second coil. And suppose I is the current. So if we represent this one, I is the current, I1. So what happened? The current is moving like this, and due to which the magnetic field inside the solenoid 1, the magnetic field inside the solenoid 1 is suppose B1, that is N1 mu naught I1. And at the same time, we know magnetic field outside the solenoid 0. Is it okay, everyone? Is it okay? Hello.
Yes, sir.
So now what happened? So we have to find out the mutual induction due to the inner coil and the outer coil. So we know the value of magnetic field. We know value of magnetic field for the inner coil means inner solenoid. B1 is N1 mu naught I1. We know it from a solenoid, a magnetic field of a solenoid. Achha. Now it is clearly visible outside this solenoid, we know the magnetic field is 0. So flux for each turn on the outer coil, flux for each turn on the outer coil, flux for each turn on the outer coil. So if we write this one is one coil and this is the second coil, so we can write flux at second coil due to the first coil and not each turn means not, suppose. So that is what happened. B1, but we are not using area A2. We are not using area A2 because outside this coil magnetic field is 0. So what we use A1. Is it clear? See, the magnetic field is present only up to the area A1. Outside the area A1, no magnetic field is there. So as no magnetic field is there, so magnetic field is 0. So magnetic field 0 into area, you get the 0. So you have a common area is only A1. So that is for flux for each turn. So total flux equals to flux for each turn into total number of turn. So flux for each turn, total flux at the outer coil 2 due to 1 is flux for each turn, that is B1 A1, and total number of turn on the outer coil is N2. Now if we put the values, B1 is how much? B1 is N1 mu naught I1. What about A1 and what about N2? N2L. See, the total number of turn, that is the number of turn per unit length into length. L is the length of the solenoid. So overall what you have, N1 N2 mu naught, N1 N2 mu naught, A1L I1. Let it be equation number 2. Now from definition of mutual induction, from the definition of mutual induction, flux at the second coil due to the first coil is equals to mutual induction at the second coil due to the first coil and current of the first coil. This is the equation number 2. So from equation 1 and 2, what we can say, at 2 due to 1, current 1, N1 N2 mu naught A1 L I1. So we can say I1 cancel. So mutual induction at 2 due to 1, N1 N2 mu naught A1 L. If you multiply it by L, divide by L, what we have, N1 N2 mu naught A1 by L1. This is my equation. And if we insert some medium, m of 2 1 is equals to, everything is same with mu naught. Now we use mu r. So N1 N2 mu naught mu r A1L, which is equals to N1 N2 mu naught mu r A1 by L. Is it clear, everyone? Is it okay?
Yes, sir.
Yes, sir.
Okay, hello.
Yes, sir.
Yes. So tell me, what is the answer? See, now we try to find out just the reverse process. Means now we are trying to find out the current. So this one means current is moving like this. Aya, ye gaya. Current ऐसे जाएगा, जाके पीछे चला जाएगा. Okay. So first of all, what happened? Your magnetic field is B2, and here you write I2, here you write IN2, and the magnetic field is like this. So now this one is not zero. Now magnetic field outside zero means here outside the solenoid magnetic field is zero. So here we write B2, that is N2 I2. So flux for each turn we write here at 1 due to 2, and we write here B2. So due to the second coil at the first coil, so we take the area A1. So you notice here one thing, area is common for both, means for both the form, means due to the 1 at 2 or due to the 2 at 1, the area is A1 in both case, and as the area is both same, so that's why you get the same result. And so total flux of each turn into total number of turn. So we write here 1 2, we write here 2 in 1, and here we write number of turn in 1. So we write here 2, we write here 2, we write here 1. So in 1 into mu naught I1 same, and this is not I1, now it is I2. From the definition of mutual induction, flux at 1, total flux, you can write total flux at 1 due to 2, mutual induction at 1 due to 2, current of 2. So here we write 1 2, current is 2, current is 2, this current again cancel. So two things we know. One is the same cross-sectional area, means the common cross-sectional area, and second thing we notice for both, the length is common, length is L for both, and as the length is L for both, so what happened, we get the same value 1 2. See, I'm just changing the data, means 2 1, now it's 1 2, data is exactly same. So if we insert some medium 1 2, exactly same. From this derivation we can say one thing, mutual induction at 1 due to 2, mutual induction at 2 due to 1 are equal. So we can write it mutual induction M. If you understand, at 1 due to 2 and at 2 due to 1, they are same value, exactly equal value. Okay, so that means mutual induction basically depend on the common area and common length. That's why their values are exactly same. This derivation is very, very important. Sometimes they say at 1 due to 2, sometimes they say at 2 due to 1. So this one is very, very important in terms of board exam. This derivation is very, very important. My next question is, I'll do one thing. My question is very, very important. So my next question is very, very important. Two coil they given you. This is the first coil. Cross-sectional area A1, length is L, and the second coil they given you. Cross-sectional area A2, length is L, number of turn N1, N2. And according to question, mutual induction for the first coil is L1, mutual induction for the second coil is L2. Self-induction for the first coil is L1, self-induction for the second coil is L2, and mutual induction is M. I repeat, self-induction for the first coil is L1, self-induction for the second coil is L2, and mutual induction is M. So proof that mutual induction is less than root over L1, L2. This question is very, very important, and this type of question, so many times they ask you 2 marks question, this type of question. So many times they ask you this type of mutual induction. So it's a very simple thing. We can write from this data the self-induction of the solenoid 1 means the inner coil. We know self-induction of a solenoid. L1 N1 square mu naught A1 L, and self-induction for the solenoid 2 second coil, that is N2 square mu naught A2L, and mutual induction we represent it M because at 1 due to 2 and at 2 due to 1 they are same value. So neither we write M of 1 2 or nor we write M of 2 1. We can write directly M. That is, we already proved it, N1 N2 mu naught, the common area A1 and length. So very simple. If we write M square by L1 L2, if we write M square by L1 L2, what we have, N1 square N2 square mu naught square A1 square L square by, we can write N1 square mu naught A1L, we write N2 square mu naught A2L, and we realize, see, N1 square cancel, N2 square cancel, mu naught square cancel, L1 L square cancel. So here you have A1 cancel. So here you have A1, here you have A2. So we write A1 by A2, and from the data it is cleared that A2 greater than A1. So as A2 greater than A1, this is less than 1. You can write here as A2 greater than A1. So what we can write, M square is less than L1 L2. So M is less than root under L1 L2. Is it okay, everyone? Can we prove it? Is it okay, everyone?
Yes, sir.
So
Yes, sir.
we can write in that manner. Next, so this question is very, very important. This derivation is very, very important. The next one is, अच्छा, तुम लोगों को एडी करंट, ठीक है, हम जब हम एसी स्टार्ट करेगा, एसी में जब हम लोग ट्रांसफार्मर पढ़ेगा तब हम पढ़ाएगा एडी करंट. Okay. So now the next question is, suppose you have two coil, one is this one, another one is this one. Number of turn of this coil is N1, number of turn of this coil is N2, radius is R1, radius is R2, R2 greater than R1, greater than or greater than. The question is that find the mutual induction due to the second coil on the first coil. As this one is very small, means it feels like a point, you can write it greater, that is better, greater than R1. So what happened, if we want to find out the mutual induction, we have to find out mutual induction due to the second coil on the first coil. As it's a very, very small, means because radius of R2 is greater than R1. So magnetic field due to the two current carrying conducting wire. So what is the formula? Mu naught I2 by 2 R2, we know this, and the total number of turn of the outer coil is N2. So this is the total magnetic field, which is on the basis of direction we can decide it is into the page or out of the page. So total flux equals to flux for each turn into total number of turn. So flux for each turn B2 into area of the one, this one, and the total number of turn of one, because we are finding at one. So what happened, mu naught I2 by 2R2 into A1 N1. So what you have, mu naught N1 into by 2R2, and A1 is, you can write pi R1 square, area of this circle. I2, let it be equation number 1. From the definition, total flux that is equals to mutual induction. You can write at 1 due to 2, current of 2, equation number 2, from equation 1 and 2, 1 to I2, that is mu naught N1 into 2R2 pi R1 square into I2. So we cancel this I2. So basically it does not depend on the current. So mutual induction, you can write mutual induction, you can write at 1 due to 2, that is mu naught N1 into by 2R2 into pi R1 square. Okay, so this one is also very, very important. Is it okay up to this? Let's try one numerical from book. See, the numericals are very simple because you have so many data, and as you have so many data, so obviously numericals are direct question. See, question number 38 from SL Aurora, page number 26.26. The question is that, what is the mutual induction of a pair of coil? What is the mutual induction of a pair of coil? Question mark. If a current changes of 6 ampere in one coil, 6 ampere in one coil changes from 6 ampere in one coil causes the flux in the second coil 12 into 10 to the power minus 4 Weber per turn, and total number of turn is 2000. Total number of turn is 2000. So it's a very simple question. This is the flux for each turn. So what is the total flux? Total flux is flux for each turn into total number of turn, that is 12 into 10 to the power minus 4 into, I think, 2000. So 24 into 10 to the power minus 1 Weber is the total flux. And from the definition we know this value is mutual induction into current. So you can understand how easy this one. 2.4 divided by 6. So I think 0.4 Henry. So you understand it's a very simple question. Next you have question number 39 from the same SL Aurora book. An EMF of 0.5 volt is developed in the secondary coil when current in the primary coil changes from 5 ampere to 2 ampere in time is 300 millisecond. Calculate the mutual induction of the two coil. See, calculate the mutual induction. So the question is that we all know induced EMF minus M di by dt, that means minus M I final minus I initial by time, which you can write mutual induction I initial I final by time. Now see, everything is given half M, you don't know, initial is 5, final is 2, and the time is 300 milli, means 10 to the power minus 3. So what you have, M 3 by 3 into 10 to the power minus 1, I guess, cancel. So m is that is equals to m into 10, which means m is 1 by 20, and 1 by 20 is how much? 0.05 Henry. Is it okay, everyone? Is it okay? Hello?
Yes,
So you have so many questions directly or indirectly. They are just a database question. If you know the formula, only one or two formula is there from the mutual induction. Nothing so much formula you have. See that if you want to know the formulas, first formula is, if you want to know the formula for mutual induction, first formula is flux is mutual induction into current. Second formula is induced EMF is minus m di by dt. Third formula is mutual induction of a solenoid is n1 small n2 mu naught. If you want, you can add mu r also for the, if you insert some medium, so mu naught mu r a1l, or you can write n1 n2 mu naught mu r a1 by l. So this one is your formula from mutual induction. Okay, now apart from that, two very important part. First part is that the mutual induction depends on orientation. What do you mean by mutual induction depends on orientation? Means as it's only it about not one coil, it's about two coil. So how you place these two coil, it depends on that factor also. So I just give you one example, then you understand. Suppose we have two mutual induction, two coil. So mutual induction also depend on how you place it. Like if you place like this, means if you place like this, so in that case their common flux is maximum, because magnetic field is maximum, means in that case the magnetic field is maximum passes, so magnetic flux is maximum. So you can say the mutual induction is maximum. So same coil, everything is same, but on the basis of placement, that is also mutual induction depend. Number two, if we put a coil in that way, and if you put another coil শুনতে পাচ্ছিস? Hello.
Yes, Yes, sir. sir.
Now see, in that case, everything is same coil, same number of turns, same cross sectional area, but the problem is that, see, the common portion decrease. So as the common portion decrease, mutual induction is also decreased. So mutual induction is minimum. Not only that, we can change or we can increase the mutual induction if we have the same area, means that for both, if you have the common area, means instead of two coil, if we use one coil, and if we wrap the secondary coil like this, and in between that, if we put primary coil exactly in between. So if we able to put exactly in between the two secondary coil, if we put primary coil, if we able to put exactly in between the two secondary coil, if we able to put the one primary coil, means then what happened, as we have two coil, so exactly the middle portion, the magnetic field is zero, because the current are in the same direction. So one is cross, one is dot. We already solve it, we already show it you. So as the magnetic field is zero, if you put there another coil, so net force apply on that coil is zero. But if you a little bit change, means if that coil is not exactly in between, a little bit left or a little bit right, that means some magnetic field is there. So extra force apply on that coil. Due to that force apply on the coil, after some time it will become heated due to the heating effect, which is called the skinning effect. Okay, so sorry, not skinning effect, skin effect. So because of that also, sometimes it's a little bit related to the eddy current also. So the coil is heated or heating effect is there. So heating effect means energy loss. So in that way, mutual induction decrease. So if you're able to put the secondary coil exactly in between the two primary coil, or if you're able to put primary coil exactly in between the two secondary coil, so then also mutual induction increase. Next, the next part is that in place of hollow solenoid, if we put some medium, like some ferromagnetic medium, so what happened then? Mutual induction is N1 N2 mu naught mu r al. So if you see this factor mu r, if you put iron, cobalt, nickel, so what you find, this one is 1000 times increase, 1000 times, 500 times increase. So if you insert some medium, then also mutual induction increase. So these are the process by using which you can use, or you can change or the value of the mutual induction. You can change the value of the mutual induction. So one thing we realize from here, and we solve it mathematically also, that M1 by root under L1 and L2 is not 1, it is less than 1. So that means this factor is called coupling factor. This factor is called coupling constant. And we realize here ki it's not 0, although it's almost 0, but it's not exact 0. M is minimum. If in your question, suppose they ask you this one, and mutual induction is maximum or minimum, you choose the right answer, minimum. But if there is a 0 answer is there, but no maximum minimum is there, then you write 0, because 90 degree to 0. But if you have a 0 and minimum option, then you choose the minimum option, because it's not 0, because at least some magnetic field is passing through this one. Okay, so that means it's exactly not 0 and it's exactly not 1, because nothing is perfect. Okay, so as it's not exactly perfect, so what happened, it's even not exactly 1. So what happened, the value of K is always in between 0 and 1, means if you multiply to self induction, and if you want to try the if you want to find out the mutual induction, means if you multiply, means what I want to say is M is never exactly equal to L1 and L2. Whatever you do, means you make it so much perfect, whatever you are able to do, but still it's not exact. So as it's not exact, so you are not able to find M is exactly equal to root under L1 and L2. It's a little bit less. Okay, and as it's little bit less, we already know it also, because some common area, or maybe some leakage and all. So that's why the K is neither perfectly 1 nor perfectly 0. It's always in between. So this is one part, how you place it, Apart from that, one more thing is there. Sometime ask in entrance exam also. Just give me 1 minute for that. Okay, so the next thing is that if we have two coil like this one, self-induction N1 and L2, and we put coil like this, self-induction N1 and L2, but the problem is that L equivalent in that case, it's a very important question, sometimes asked in entrance exam, L1 plus L2 plus 2M, and here it is L equivalent is L1 plus L2 minus 2M. So now you have a question, I guess, why this thing happened. So it's because of the orientation. See here, the direction of current in both the coil are in the same direction. But if we see this one, here the direction of current, they are opposing each other. So when the direction of current, flux is common, but as it is reverse, so it will be reverse happening. Means here the net magnetic field is decreasing nature, and here the net magnetic field is additive nature. So what happened here, mutual induction is opposing, and here the mutual induction is supporting. So what happened? What happened in this one? Total mutual induction L1, total inductance L1 plus L2 plus 2M, and here L1 plus L2 minus 2M. So on that basis, if you send some amount of current like di by dt, and we know induced EMF is L di by dt or M di by dt with negative sign. So we make it L di by dt, means if we multiply both sides, minus L1 di by dt minus L2 di by dt minus 2M di by dt, means we multiply by minus di by dt both sides. So what we have, total equivalent EMF due to the L1, equivalent EMF due to the L2 plus 2 equivalent EMF due to the M. And here what happened, exactly the reverse thing happened, minus L equivalent di by dt, that is minus L1 di by dt minus L2 di by dt. Now this one, minus of minus is plus. So plus 2M di by dt. So what you have, equivalent, that is equivalent L1, equivalent L2 minus 2 equivalent, sorry, this. So this is one more thing related to mutual induction. They can ask sometime the total EMF, they can sometime ask the total inductance in this two type of question. So you can solve or you can understand. They even give you the value. Suppose this is 20 Henry, this is 5 Henry, and mutual induction, mutual is, suppose they said 2 Henry. So they can ask you in this way also. Suppose L1 is 20 Henry, L2 is 10 Henry, and M is suppose 2 Henry. So in that case, what happened? A total equivalent is how much? 20 plus 10 plus 2. 2 into 2, that is 34. And here L equivalent is 20 plus 10 minus 4, that is 26 Henry. So you understand the difference between these two. Is it okay? Hello. Respond.
Yes, sir.
Okay.
Yes, sir.
So it's very, very important. Although the problem is that now we realize that for mutual self-induction, for induction, if we put two coils, so not only the self-induction, also mutual induction is also calculated. So basically, sometime examiner they give you this type of question, although they don't give it, because indirectly it's a wrong question, because if they given you coil and if they just put they ask you what is the self-induction, so obviously in that coil mutual induction is also there. Okay, so indirectly it's a little bit wrong type of question. So that's why mostly examiner not try to give it, but sometimes some examiner may give you, they just want to check you that you know it or not, what is the values of self-induction in series and what is the value of self-induction in parallel. Although I'm sure they don't give it, but it's not perfectly okay. If you write this is the answer according to examiner, it's not exactly right, because with self-induction you have some mutual induction also, and as they don't give you the mutual induction, so it's not possible to find out, but still they give you. So that's why I'm write it, and that's why I'm write it at the last. If you have self-induction in series, no mutual induction is there, okay, just self-induction. Although it's not possible, you have more than one coil, and if the examiner I am asking what is the net self-induction without mutual induction, means the net inductance without mutual induction is not possible, but here we just ignore the mutual induction, we need just the self-induction. So in that case, di by dt, so induced EMF 1, 2, 3, it's same like resistance. So total EMF E1, E2, E3. So minus L di by dt, that is minus L1 di by dt, minus L2 di by dt, minus L3 di by dt. So what we have, L equals to L1 plus L2 plus LC, because you realize it's same like resistance, but I'm again saying this is not the exact answer. This is not the right answer, because with this self induction you have some mutual induction. But if the examiner asks you to ignore the mutual induction, just find out the self induction, then they can give you this type of question. Okay. Similarly, for mutual induction, what happened? Sorry, for parallel connection, what happened? Okay. This is the di by dt, and this is di by dt. Di by dt. L1, L2, L3, di1 by dt, di2 by dt, and di3 by dt. So total di by dt, that is di1 by dt, di2 by dt, and di3 by dt. Right? So now if we want to find out di by dt, so what we have, induced EMF is minus L di by dt. So minus equivalent by L1. For parallel connection, voltage is equivalent by L2. L, that is L1 minus equivalent by L2 minus equivalent by L3. So 1 by L is 1 by L1, 1 by L2, 1 by L3. But I'm repeatedly saying they don't give you this type of question. So, but if they give you, just they give you the very simple structure. They don't enter into the complex structure, because if they enter into the complex structure, the problem is that so much mutual induction arises. So which examiner also try to ignore that portion, because without mutual induction, the self induction is not possible when you have so many. So they try to ignore that part, series and parallel part. If they want to give you, they give you from the circuit, means a current portion. Okay, so that is my today's class, and I'm trying to